In this research paper titled Credible Plan-Driven RAG Method for Multi-Hop Question Answering, the authors from Macau University of Science and Technology introduce a new framework called PAR-RAG, which stands for Plan Then Act and Review Retrieval-Augmented Generation. This method is designed to tackle the challenges of multi-hop question answering, a task that requires piecing together information from multiple sources through several steps of reasoning. Multi-hop question answering involves answering questions that can't be resolved with a single piece of information. Instead, it demands integrating data from various places and performing logical steps to arrive at the final answer. This is common in areas like complex decision-making or in-depth analysis. The paper builds on Retrieval-Augmented Generation, or RAG, which is a technique that combines retrieving relevant information from a database with generating responses using large language models. However, current RAG methods often struggle with errors. For instance, if the initial step in reasoning goes wrong, that mistake can spread and grow worse through subsequent steps, leading to inaccurate final answers. The authors point out two main issues. First, deviations in the reasoning paths, which happen when the query isn't broken down correctly at the start, and second, errors in intermediate results, caused by things like irrelevant data interfering or conflicts in the information used. To fix these problems, the PAR-RAG framework organizes the process into three key stages: planning, acting, and reviewing. In the planning stage, the system takes a top-down approach. It starts with a broad view of the entire question and breaks it down into a series of logical, interconnected steps. This is like creating a roadmap before starting a journey, ensuring that the overall path makes sense and avoids getting stuck in local dead ends that might occur in traditional methods. Once the plan is set, the acting stage kicks in. Here, the framework executes each step of the plan while incorporating multi-granularity verification. That means it checks the results at different levels of detail. First, it uses coarse-grained similarity, basically, looking for information that's broadly related to the current step, to generate a preliminary answer. This helps build a basic understanding. Then, it dives deeper with fine-grained data, which is more specific and richly connected to the subproblem. As it goes, a cross-verification mechanism refines these interim results, catching and correcting errors to prevent them from building up. The review aspect is woven throughout, ensuring that each intermediate result is accurate and aligned with the original plan. This incremental checking mimics how humans handle complex tasks, drawing inspiration from cognitive frameworks like the PDCA cycle, which stands for plan, do, check, and act. In human problem-solving, we first understand the big picture, break it into manageable parts, execute with verification, and adjust as needed. PAR-RAG aims to replicate this by creating an interpretable and reliable reasoning process that minimizes error propagation. The paper explains that in the global planning phase, complex questions are decomposed into subproblems that are logically linked but can be solved independently. This helps construct a coherent path and prevents the system from veering off course. During the plan execution and verification phase, if there's not enough local information, the system retrieves broader, semantically similar data first. Then, guided by that, it fetches more detailed data for refinement. This multi-layered approach ensures that the reasoning trajectory is error-constrained, meaning mistakes are caught early rather than amplified later. To evaluate this framework, the authors conducted experiments on multi-hop question answering datasets. The results show that PAR-RAG significantly outperforms existing state-of-the-art methods. Specifically, it achieved higher scores in key metrics like exact match, or EM, which measures if the answer is precisely correct, and F1 scores, which balance precision and recall. These improvements highlight the framework's effectiveness in handling the complexities of multi-hop QA. The paper also touches on how humans excel at these tasks through structured cognition. Unlike AI, which might jump straight into answering, humans plan holistically, execute step by step with checks, and refine as they go. By adopting this, PAR-RAG bridges the gap between human-like reasoning and automated systems. In terms of keywords, the paper lists RAG, open domain question answering, multi-hop reasoning, and large language models, emphasizing its focus on advancing these areas. Overall, this work demonstrates that by emphasizing careful planning and verification, PAR-RAG provides a more credible and accurate way to handle multi-step queries, paving the way for better AI performance in real-world applications.